All right, so get this. You want to understand the science behind those large language models, right? Well, we dug into this research paper called Physics in Next Token Prediction. And let me tell you, it's blowing my mind how they're linking AI learning to actual physics.
Yeah, it's some pretty groundbreaking stuff. They're introducing these two laws to describe the whole process. The first law of information capacity, which deals with how information is conserved during training, and then the second law, which dives into the energy dynamics of it all.
Whoa, so if I'm understanding this right, they're saying there's like a real connection between the physical world and how AI learns. That's wild. But before we get too deep into those laws, maybe we should start with the basics. What exactly is next token prediction? And why is it so important for these large language models?
Great point. So next token prediction, it's essentially the heart of how these models work. It's like histogeisha. Imagine the autocomplete feature on your phone, but on a much grander scale.
Yeah.
The model takes a sequence of words, or tokens, and tries to predict what comes next. The better it gets at this prediction game, the more we say it understands the language.
Yeah.
And the information it's been trained on.
Okay, so it's all about making these accurate predictions, but how does that connect to the idea of physics? The paper mentioned something about information compression, right?
Exactly. They use this clever analogy to explain it. Imagine trying to send this huge data set from one place to another. If you're not being smart about it, you just send the whole thing, which takes a ton of bandwidth and energy. But what if you could compress that data first, like creating a zip file? That's where the intelligence comes in.
So a really smart AI model
Yeah.
would be able to compress the data really well. Like it's figuring out the most efficient way to package all that information.
Precisely. And the smaller the model can make that file by predicting the next token accurately, the more we can see its intelligence shining through. It's like it's figured out the underlying patterns and structures in the data, which allows it to represent the same information in a much more compact form.
That's a really cool way to think about it. So where does this first law of information capacity fit into all of this? The paper throws around this formula, but I'll be honest, I got a bit lost in all the symbols.
Don't worry. The formula itself can be a bit intimidating, but the core concept is actually pretty straightforward. The first law essentially says that information doesn't just disappear, it gets moved around.
Okay, so it's kind of like that law of conservation of energy, but for information.
You got it. As the AI model learns, meaning it gets better at predicting the next token, information is being transferred from the dataset into the model itself. It's as though the model is gradually absorbing the essence of the dataset.
So the more the model learns, the more information it's pulling from the data it's trained on.
Exactly. And this process is dynamic, meaning it's constantly changing during training. The model's information capacity, or how much information it can hold, increases as its prediction accuracy improves. It's like watching a sponge soak up water.
Now, that's an analogy I can get behind. But this whole idea of measuring how much information the model has absorbed seems pretty tricky. How do you even quantify that?
That's where the formula comes in. It gives us a way to actually measure the information capacity of the model and how it changes throughout the learning process. Yeah. It takes into account things like the size of the model, the amount of data it's trained on, and its prediction accuracy.
So it's not just about how much data you feed the model, but also how effectively the model can extract information from that data.
Absolutely. It's about the quality of the learning process, not just the quantity of data. And here's where it gets really interesting. The paper suggests that you can actually use the initial prediction error of the model to estimate the quality of the data set itself.
Wait, so you can judge the data set by how wrong the model is at the very beginning? That seems kind of counterintuitive.
It does, right? It's like judging a book by its cover. But in this case, it's scientifically valid. A higher initial error might actually indicate a richer, more complex data set. Think of it this way. If the model is struggling to make accurate predictions early on, it suggests that the data set has a lot of nuanced information for the model to learn.
Okay, now that's a mind-bending idea. So a dataset that throws the model off at the start could actually be a good thing because it means there's more to learn.
Exactly. It's all about recognizing that a challenging dataset can lead to a more sophisticated understanding in the long run. It's like giving the model a tougher workout so it can build stronger mental muscles.
So we talked about information capacity and how it relates to the model's learning process. But there's another piece to this puzzle, right? The second law of information capacity. And this one deals with energy, if I remember correctly.
You're exactly right. And this is where the real-world implications start to hit home. Hashtag TTS, the Deep Dive episode 2024-1222, part 2 of 3. So the second law of information capacity it gets into the nitty-gritty of how much energy it actually takes to train these AI models.
Yeah.
And it's not just about plugging them into a wall socket, It's about the fundamental energy requirements tied to the very act of learning.
So you're saying there's a real energy cost associated with making these AI models smarter. That's something I hadn't really considered before.
Yeah, it's a crucial factor, especially as these models get more and more complex. The more information a model learns, the more energy is required to facilitate that learning. Remember how we talked about the model's information capacity increasing? Well, the second law essentially says that increasing that capacity is not free.
That makes sense. It's like building a bigger house. You're going to need more materials and energy to construct it. But how does this explain the need for those massive data centers we always hear about?
Those data centers are essentially tower houses, designed to feed the energy demands of these massive AI models. Training them takes a tremendous amount of computational power, which translates directly into energy consumption.
Yeah.
And there's a theoretical limit to how efficient this process can be, even with the most advanced technology.
So even if we had like super efficient computers, there's still a fundamental energy barrier we can't break. That's kind of a bummer. What sets this limit?
The limit is rooted in a concept from physics called Landauer's principle.
Yeah.
It's a bit complex, but the gist is that erasing information, even in a computer, requires a minimum amount of energy. And every time a model updates its understanding during training, it essentially has to erase some of its previous knowledge to make room for the new stuff.
So it's like cleaning out your closet to make room for new clothes. You have to get rid of some of the old stuff to make space. But in this case, even getting rid of information requires energy.
That's a great way to put it. And that energy cost adds up, especially when you're dealing with AI models that are constantly learning and updating their knowledge base.
This whole connection to physics is really eye-opening. It makes you realize that AI isn't just some abstract concept. It's grounded in the same physical laws that govern the rest of the universe. But it also makes you wonder, are there any ways to get around this energy barrier? Could we find a way to train AI that doesn't require so much energy?
That's $1 million question.
Yeah.
And one that researchers are actively exploring. What if we could find a way to make the learning process more efficient? Maybe by minimizing the amount of information that needs to be erased, or by finding entirely new ways to represent and process information.
It's like searching for a loophole in the laws of physics. But hey, if there's one thing we've learned from scientific progress, it's that we should never underestimate human ingenuity. So while this Landauer's principle sets a theoretical limit, maybe there are clever ways to work around it, or even redefine the rules of the game entirely.
Absolutely. The paper itself acknowledges that there might be alternative approaches to AI training that could sidestep these limitations. It's a call to action for the scientific community to think outside the box and explore new frontiers.
It's exciting to think about what the future holds for AI, especially if we can find ways to make it more energy efficient. But for now, let's bring it back to the paper and talk about some of the other insights it offers. The authors mention this concept called lossless quantization, which sounds pretty technical. What's that all about?
Lossless quantization is actually a really clever technique for making AI models more efficient. It's all about finding ways to compress the model's parameters without losing any of the information it has learned. Think of it like shrinking a digital image to save space on your computer.
Okay, so you're basically trying to make the model's brain smaller without sacrificing its knowledge. But how do you ensure that you're not losing valuable information in the process? It seems like a delicate balancing act.
It is. Compress too much, and you risk degrading the model's performance. But the paper provides a condition for lossless quantization, a mathematical formula that ensures you're not squeezing out too much information. It's like finding the sweet spot between efficiency and accuracy.
So it's not just about blindly shrinking things down, but about doing it in a smart way that preserves the model's intelligence. It's amazing how they've managed to connect these concepts from physics to the practical challenges of building AI systems.
It's all about recognizing the fundamental principles at play. And the paper goes even further, highlighting how these laws of information capacity actually align with other established research in the field of AI.
So these new ideas aren't just coming out of nowhere. They're actually fitting into a larger picture of how we understand AI. That's reassuring. What other research do they connect with?
One example is the scaling law for neural language models. This law is based on empirical observations, shows how the performance of these models scales with factors like the size of the data set and the computational power used for training.
So the fact that these new laws of information capacity align with what researchers have already observed in practice gives them even more credibility. It's like finding different pieces of a puzzle that all fit together perfectly.
Exactly. It's all starting to make sense. in a more unified way. And the implications are huge. If we understand the physics underlying AI learning, we can potentially develop new and innovative ways to train models. Maybe even ways that bypass some of those limitations we discussed earlier.
It's like unlocking a whole new level of understanding. And speaking of understanding, the paper also delves into another fascinating concept, the knowledge capacity scaling law. This one seems particularly relevant to our discussion about how much information these models can actually store.
It is. Essentially, this law suggests that despite their massive size and complexity, large language models actually store surprisingly little information per parameter.
Wait, really? So all that data, all those parameters, and they're not storing that much information individually. That seems kind of counterintuitive. We've been talking about them absorbing information like sponges.
It does, doesn't it? But think of it this way. The human brain has billions of neurons. But it's not as if each neuron stores a specific memory or piece of information. It's the connections between neurons, the patterns of activation that hold the real knowledge.
So it's not about the individual units, but about the network as a whole. It's about how those individual components work together to create something greater than the sum of their parts.
Exactly. And this is where the concept of emergence comes into play. When you have a complex system with many interacting parts, like a large language model or the human brain, new properties and capabilities can emerge that aren't present in the individual components themselves.
That's a really profound idea. It means that the real magic of AI lies not just in the sheer number of parameters, but in the intricate web of connections and relationships that emerge from their interactions.
Precisely. And that's what makes these large language models so fascinating. They're capable of doing things that we never explicitly programmed them to do. They're learning and adapting in ways that we're still trying to fully understand.
So while we're getting a better grasp of the underlying physics, there's still a lot of mystery surrounding how these models actually develop their knowledge and abilities. And we've created these incredibly powerful tools, but we're still figuring out how to use them to their full potential. But there's one thing that keeps coming up in our discussion about data. We've talked about data size, data quality, and even the energy cost of processing all that data. The paper also touches on a really important point about the limits of just throwing more data at a model. Can you elaborate on that a bit?
Absolutely. One of the key takeaways from this research is that simply scaling up models and data sets isn't always the answer. It's not just about having big data. It's about having smart data. Hashtag TTS The Deep Dive episode 2024-12-22, part 3 of 3.
So it's not just about quantity, but quality and strategy when it comes to training these AIs. It seems like there's this misconception that if you just keep feeding an AI more and more data, it'll just keep getting smarter and smarter. But this paper suggests that's not necessarily the case.
Right. Remember those energy constraints we discussed earlier? Throwing more data at the problem can lead to diminishing returns. You might see smaller improvements in performance, while the energy costs keep rising. It's about finding that sweet spot between data quantity, model complexity, and the energy required for training.
So it's like overfeeding someone. Just because you keep giving them more food doesn't mean they're going to become healthier or stronger. There's a point where it becomes counterproductive.
That's a great analogy. And there's another risk associated with too much data, overfitting. If you train a model on an excessively large data set, you can become too specialized, too good at recognizing patterns in that specific data set, but less able to generalize to new information. It's like teaching a student only one subject. They might ace the test in that subject, but they'll struggle when faced with something new.
So a model trained on a massive data set might end up being a one-trick pony, unable to adapt to new situations or learn new things effectively.
Exactly. It's like becoming so accustomed to one particular maze that you get lost in any other maze, even if the basic principles are the same. We want models that are both knowledgeable and adaptable, capable of transferring their learning to new challenges.
So it sounds like there's a real art to curating the right data set for training these AI models. It's not just a matter of gathering as much data as possible, but selecting data that's relevant, diverse, and representative of the real-world scenarios the model will encounter.
Absolutely. And this is where human expertise is still absolutely essential. We need experts who can carefully select, clean, and organize the data to ensure that the models are learning the right things. It's like a master chef selecting the finest ingredients and preparing them in a way that brings out their full flavor.
So we're not just building AI, we're shaping it. We're responsible for guiding its development, ensuring that it learns effectively and aligns with our values. That's a pretty profound responsibility.
It is. And it's one that we need to approach with both enthusiasm and caution. We need to be mindful of the potential risks, but also excited about the possibilities. AI has the potential to revolutionize countless aspects of our lives, from scientific discovery to creative expression, but it's up to us to ensure that it develops in a way that benefits humanity as a whole.
You know, this deep dive has really opened my eyes to the complexities of AI, especially this often overlooked connection to the physical world and the laws of physics. It's fascinating to think about how these fundamental principles of information and energy are playing out in the development of this groundbreaking technology.
And it's important to remember that this is just the beginning. We're still in the early stages of understanding the true potential of AI, and there are countless avenues for exploration and discovery ahead. We need to keep asking questions, challenging assumptions, and pushing the boundaries of what we think is possible.
Absolutely. This paper has given us a lot to think about, a new framework for understanding how AI learns, and the challenges and opportunities that lie ahead. But before we wrap up, I want to bring up one more point that really struck me. The author suggests that we might be able to bypass some of these limitations we've been discussing, particularly those related to energy consumption, if we could find a fundamentally different way to train AI. That's a pretty bold statement.
It is. It's like asking if we can rewrite the laws of physics as they apply to information processing. But it's a question worth pondering. What if we could move beyond the current paradigm of information transfer and erasure? What if there are other ways for AI to learn that don't rely on these same energy-intensive processes?
It's like imagining a world where energy is no longer a limiting factor for AI development. What kind of breakthroughs would be possible if we could tap into a different kind of learning process, one that's not bound by these same constraints?
It's mind-boggling to think about. This paper challenges us to question our assumptions and to envision a future where AI might operate under a whole new set of rules. It's a call to explore uncharted territory, to think beyond the limitations of our current understanding.
Well, on that note of boundless possibility, I think we'll wrap up this deep dive. It's been an incredible journey, exploring the intersection of AI and physics. I feel like we've only just scratched the surface, but we've laid a solid foundation for understanding the fundamental principles at play.
And I hope we've sparked a sense of curiosity and wonder in our listeners. The world of AI is full of mysteries, and it's up to all of us to keep exploring, keep questioning, and keep pushing the boundaries of what we know.
Beautifully said. So to all our listeners out there, keep learning, keep dreaming, and never lose that spark of curiosity. Who knows? Maybe one of you will be the one to discover that revolutionary new approach to AI learning. Until next time.